Right. Right. So this was the first question. A number of total training images in a 5-way 10-shot episode for few shot learning. So if you have a 5-way 10-shot episode, it means that you have 5 classes and 10 training samples per class. So a total of 50 images. Okay. So that was the answer, 50. Now the next question. In generalized zero-shot learning is a model judged on the classification accuracy on the unseen classes. The answer will be false because for generalized zero-shot learning, it is judged on the classification accuracy in all the classes, seen as well as unseen classes. So, and for generic, I mean general zero-shot learning, I mean not generalized, simple zero-shot learning, this would have been true, but not for generalized zero-shot learning. Right. Next question is on, I mean, using distillation basically, or say transferring knowledge from teacher to a student network. So student network will be trained on which set of losses? The student network has to incorporate both the classification loss, okay, as well as the distillation loss. So the answer would actually be your, let me see, it was supposed to be NB. Okay. So it was a cross entropy loss, and in place of distillation loss, you are using the Kale divergence version of the distillation loss, because this are random terms which I just simply crossed two of these things and created losses like that. But the answer would be A and B. Next, in multitask learning, the model is shared by multiple tasks. Specifically, which of the following is true? So if you remember that when we were discussing multitask learning, the initial layers were fixed and the final layers were dedicated to each of the tasks. So this negation statement, final layers are not shared, would be true because the first statement is not correct. Final layers are not shared. This is also not correct. Only middle layers are shared, and this is also not correct. Only initial layers are not shared. So only the final layers are not shared is correct. Now the next question that comes up. Say, I mean, you would have come across gradient reversal layer in your domain adaptation, and its objective was to reverse the direction of the gradient, but this reversal of gradient direction would happen during the backward pass. During the forward pass, gradient GRL would behave just like an identity function. If you remember, we had discussed this. And so among A, B, C, only A and C would be correct. Okay, so only sentences A and C are correct. Other options will be not be correct in this particular set. Now, for the next question, unstructured pruning leads to sparse parameter weight matrices. Unstructured pruning can achieve better compression as compared to structured. So both of these items are true because your unstructured pruning will remove any. I mean, you take your weight matrix, and depending on the magnitude, it can remove any of the weights, regardless of whether it is following some structure, removing one particular neuron at a time or one particular filter at a time. Doesn't follow any such structure. So as a result, it will be able to reduce the model parameters, or at least reduce the computation required for those model parameters to much better extent as compared to a structured pruning, because structured pruning will always be restricted to removing entire neurons or entire filters at a time. So if that particular setup leads to a sudden drop in loss or a major loss, your structured pruning will not be able to delete that particular, say, filter. It can only delete a particular filter or a node when it is not as useful as the others that are already there. So, but obviously, structured pruning will still allow you to use all the acceleration methods that are used for making your processing faster of your neural networks, whereas unstructured pruning will does not have any uniformity in which it's deleting I mean parameters, so that way you'll have to come up with separate ways of making the processing faster for unstructured pruning.
Sir, but the compression that it has asked, isn't the compression more in unstructured?
Yeah, it is more.
So it
Unstructured
should
is
be
HV.
B should be true, sir.
A is also true, no? Both are true. Both A and B are true.
But it is asking which one will have.
No, what is the question? I didn't get your question. The options are, which of these options are correct? So either both A and B are true, either both of them are false, either only A is true or only B is true.
Understood, sir.
Okay. Next question. Consider the task of parameter quantization, which basically quantizes the weights of your parameters in the model and brings down to a lower precision level so that you can work with lower precision and lower computation. Okay. So for this, you had to basically remember the formula that we had basically used for, achieving the scale and Z values of your given system of symmetric quantization. And if you remember that, you would remember that I can also maybe share that screen. Share it so that's better. Yeah. So if you remember this, in this particular setup, you're using all the values except the quantized minimum value. Quantized means minimum value, which was basically the answer for this particular question. Okay. So you're not using the minimum value of the quantization range. And this question, a lot of people had a lot of doubts because there were actually two confusing options. So both this option, which is 30 cross 30, so 30 cross 30 is 900. So a compression ratio of 3 is you're trying to get parameters down to 300. So the two matrices that you get, 30 cross 5 and 5 cross 30, which is, if you add them up, you get 300 parameters. But if you look at the other option, that is 60 cross 60, which is your 3600, and you try to bring it to 1/3, so it's 1200 parameters. So even in this case, you will see that if you add these two up, you'll get 1200 parameters. The reason why this is not the option is because if you look at this particular decomposition, 60 cross 8 and 12 cross 60, this is not a valid decomposition of 60 cross 60 because you cannot get back the original matrix from here. Whereas in this case, you can simply multiply these two matrices and you get back a 30 cross 30 matrix. So this was just to give you one option which satisfies in terms of matrices, but is not a valid decomposition as such. So that's why I had given this option. So there was this confusion. People were asking if there are multiple correct answers. It was not. There was only one correct answer in this particular set. Okay. Okay. Next question is, in the context of graph and graph neural networks, which of the following is true? So input to subsequent layers of graph neural networks only includes the successor vertices of the vertex processed by the current layer, which is not true because if you remember that we updated the representation of every node at every layer. So the only thing that was different was that during this updation, it was using the values of all the neighborhood nodes of that particular vertex, and also connect using the current previous value of its current value, but you are updating the representation of every node feature. So this is not true. Graph neural networks can process images. It's true because you can basically represent an image, as we had discussed while discussing why a convolution network can't be used for graphs. As that your image is basically a structured graph. You have a very definite structure. You already know which are the neighbors of a particular pixel, and that way you can design a graph based on and any image, and then basically run it through a graph neural network. Another sentence was graph neural network encodes the graph to give another graph with reduced number of vertices, which was not the point. Remember, the point was that it would give you another graph where the same vertices, the representation of features of these vertices would be in a lower dimensional space. So where again the same property would be satisfied, that is, if two nodes are neighbors in the original graph, even in the lower dimension representation, the nodes will still be neighbors. So the number of vertices will not go down. the next point was that graph neural networks are useful when all the vertices of the graphs are disconnected. So the whole point of using a graph neural network was to so that you can utilize your neighborhood information and accumulate them when you create a new layer. You're accumulating all the neighborhood information as well as you're updating the using the previous features of that particular node. Now, if there are no when all the vertices are disconnected, which is there are no connections or edges between any of the vertices, you're simply applying one single fully connected layer to every vertex feature, and then there is no use of GNN as such. You can simply learn one fully connected layer and pass your every node through that fully connected layer, and you'll learn some representation for that. So it will not be this particular network will not be of any use to it because there is no use of your graph structure itself in your in such a graph where there is no connections between the vertices. Okay, and the final question was in ICAL method of incremental learning. If we discard, so whenever we have to include say 10 exemplars from a new class, remember the herding strategy with which we had discussed in the ICAL method. So if I want to, so if I see a new class and now I want to back up a few of the examples of that class so that in future I can use those examples. How do I put those new samples? So I had to create some space from the existing say exemplar set. So in the exemplar set, if I had to create a space for 10 samples, I would first of all divide it by the number of classes that I already had in the exemplar set. And say, suppose I already had 5 classes. So I would remove 10 by 5, which is 2 samples of every class. And also, we would not remove the first set of samples from any class. We'll actually remove the last set of samples. So remember when we were picking the samples in the exemplar set, we were taking it in the higher priority order. So the earlier images would be more relevant to your classes compared to the later images. So at any point of time, if you want to reduce the set of exemplars in your exemplar set, you remove from the end of that particular class and not from the beginning of the class, because beginning images are the most useful ones. Okay. So therefore, this statement will again be false, right? So these are the set of results, and I'll release the
Can you go
yeah,
to the fifth question answer?
fifth question.
The
Which question can I?
gradient reversal.
Gradient reversal. Oh, sorry. Yeah.
So I think the answer is a second one, right?
This one?
Yes, sir. Okay.
A and C.
Okay, sir. Yeah, thank you.
So you already have, I think you must have gotten an email, everyone, about
No,
your
no, sir.
submitted.
I did not get email. I told you last time also.
You still did not get it. Achha, but your submission is there, as far as I remember. Let me
Yeah,
again
submit,
check.
but I didn't get the email.
Achha, that's fine. That's fine. I mean, let me just check once. Your submission is there. What's the email ID? Let me look at the email ID that you provided.
M23 CSA 522.
Yeah, no, that's fine. You added wrong email ID. You added m23csa522@gmail.com. So that's why you did not get
Oh, sorry
the
about that.
uh,
But answers are there, no?
answers are there. Answers are
Oh, sorry about that.
there. Okay.
That's why it was giving that pictures.
No, pictures I think a lot of people got. That was for the captcha. I don't know why they included captcha in the form. Okay. So let's continue with our lecture.
Sir, one request from you before we
Yeah.
start the class.
Yeah.
That is not related to class. We just want to convey to you. So, you are providing a course in the next semester, which is a computer vision, right?
Vision, yeah.
So, is there any limit on that for maximum number of students? Because a
Yeah,
lot.
this time, in lot of courses in CSE department have been added with a limit because there is a sudden. First of all, it's a hybrid course. Otherwise, there we would not have had a limit as such. but there is a severe restriction on the number of TAs that we'll be getting next semester. So
But sir,
lot of courses.
this is our core subject.
This is your core subject?
Computer vision is machine
It is
learning and
not
your
course,
elective.
core subject. It is just elective. Yeah.
Elective.
no, I mean to say, in terms of knowledge, I am telling this is important subject for all of us. In terms of
No, I
domain,
get that, but the point is that we don't have enough thing. But I think your deep learning course would have been. I mean, because see, I think if you look at the syllabus for vision as
so
well,
in deep
it is
learning, only basic CNN was covered. So in terms of algos, which are like YOLO and other things, which are basically for the object detection and other things, these were not covered there.
no. So if you look at the syllabus for computer vision, 95% of it is traditional ML based or traditional vision based. This thing processing of images and all. So that's the one very genuine confusion a lot of people are having. It's you will be dealing with traditional setups. I mean, without using neural networks or anything. And the only topic that comes up at the end is, I think, on YOLO, which is at the end. I mean, it's 1 or 2 lecture only. So the rest of it is fully traditional vision.
There is one more issue, sir. Like, since we are in the executive program, we can only opt for subjects that have been offered. This time around, nothing specifically for us has been offered, except for those 5 hybrid subjects.
Okay.
So
So
if
that,
we can't even choose the hybrid subjects, then it becomes an issue because
I
nothing
think-
has been given to us in
I
normal
think
from CSC
among the
department.
hybrid subjects, I think not all have had that restriction. So I think, as I remember, this course that Dr. Sumit Kalra has offered, that has
Even that
very
has
high-
got the restriction. I mean, sir, I mean, we are forced to take some non subject which are not related
Because
to our course.
we can't take the routine subjects, sir. We can only opt for subject particularly offered for executive, which this time around CSC department has not done. And the second option, that is a not very suitable option, but doable option, is a hybrid class. That has got a restriction, and by the time we opted, we couldn't opt that also. So it ends up we not getting to opt anything.
We are only
Vis-a-vis a
getting
person
like
attending the college might be able to opt for from out of the so many options available with them. Hybrid is an add-on. For us right now for this semester, hybrid is the only option that we have been given
So,
by the department.
Have you discussed this with your this thing? The
We are
faculty?
following
We
up on the
haven't been
email.
able to get in touch with the faculty advisor, sir. Nitin sir से बात नहीं हो पाई है, so that has been an issue.
So, but this is a
Because
serious issue for
this
all
was
of us.
supposed to be managed by him. I mean,
I
We
don't.
we
so that you
understand, sir,
have
but
enough.
since that is a subject that seems to be something that we a lot of us want to pursue, and that is one of the few options that we have. We don't have any other option also, sir. There are only 5 options available
Currently,
with us.
yeah, I understand, but currently the situation with CV is a very tricky situation. So I'm not sure if I'll be able to expand it any further at this point, at least at this point. There are some other administrative issues also involved in that particular course. So that's the
The
problem.
only submission is if you could, sir, at least convey this is the point coming from this particular batch, sir. We
Yeah,
don't
actually,
have too many options this time around, sir.
Yeah, I
Only
get that.
hybrid
So
courses are
maybe
available with us.
I'll ask Nitin to follow up, because I think he's also new. Maybe that's why he's not following up on this particular thing. So
Possibly,
yeah,
sir. Possibly, sir.
yeah. So maybe
I
if
also
some more courses can be given up. I mean, as a hybrid or some other option.
I have a question. In a hybrid mode, when the exams are conducted, for the online student, the exam will be conducted in an online manner, or again we have to come over there and.
That was my understanding, but this thing changes from time to time. So the faculty advisor may be able to confirm this. But my understanding was that this too happens parallelly. The regular students give regular exam in physically, and the others give it online.
Yes, sir.
But then this has to be confirmed by your faculty advisor.
That was confirmed last year, sir. Means the beginning of first semester. So
Achha.
for us, it will all be online, and
Okay.
whatever is the hybrid thing, we will be doing parallelly with people
That
giving
was
the
my
exams.
understanding also.
Yes, sir.
So
That's how it is happening, sir.
okay.
Another question I have is like I had computer vision during my masters. I'm a PhD student, so Can we do a repeat of the course? Is it allowed?
You had computer vision. No, that depends on the requirement. You're a PhD student, no? So
Yeah.
you don't. I mean, you just have to pick any 4 subjects for your.
Yeah. Yeah.
Yeah, but that was masters from a different college, right?
It was from IIIT Hyderabad.
Okay. So it depends on your advisor then. If your advisor is okay with you having already pursued that early on, then you might, because it's up to you. In PhD, you don't have restrictions on courses that you do.
On courses. Okay.
Yeah.
Okay.
Okay.
So, but just a humble request from our side. A lot of people in our batches are interested in your course. So if you can
Yeah.
expand it even with few seats, I mean, some of us will get.
Yeah, the biggest problem, I get that. The
But we
biggest
agree,
problem is
sir.
that,
See, in your course, we don't require a
in
lot
fact,
of assistance from TAs also.
in
To be
fact,
very
what I
frank.
actually did was that I had initially there was a cap and I had increased the cap, I think yesterday, and within 1 hour that cap got filled, and again people started asking for increasing cap. So it's a very tricky situation right now. So let's see.
Yeah, because
Sure.
so, in terms of projects and all also, I mean, to be very frank, we don't rely much on TAs. I mean, okay, some guidance will be there here and there, but only thing will be the exam conductance, and that will be the issue for you. But apart from that, all the learnings can be taken
See,
care by ourselves.
I get that, but the problem becomes because it's a hybrid course. See, when I'm expanding a cap, there is no way to expand, at least now, to expand the cap only for executive students. If I
Yeah.
could have done, if I had that option, I would have done it. The
Yeah,
point is,
that-
if I have to, if I have to expand a cap in this hybrid course, I have to expand it for all students, and that's the problem actually. Even before you fill up, the regular students get to know these things much faster.
So
They will
this can be
immediately.
taken care by the faculty, no? Okay, only for executive, at least for our batch.
At least up to this point, we cannot put in any such restriction as such. That is the problem. I cannot say that I'll only take further. If I open it up further, I'll only take now executive students. So at least at this point, I don't have that option.
Sir, if you
If
need
during
TAs and all,
registration before
one of
registration
us,
we get such an option, I can do that. But not as of now, there is no such option.
if you need TAs and all, we can provide one of our volunteer. There are people in our batch who are expert in this domain, so they can
That's
take care of
not the
that.
problem. I need TAs for physical students more. So for executive students, anyways, I might get a few TAs. Okay, but the problem is as soon as I expand the size of the course, there is a 99% chance that even before you fill anything, the regular students will fill up that space, and that has been happening. That has already happened once. So when I expanded the space, suddenly within 1 hour, and also this process itself is long. I send in a request, then they take I think a day or a half a day to increase the thing, and suddenly out of nowhere, I don't know how people get to know. Maybe the regular students keep trying and all, and within an hour it got filled. So that's my primary concern is I don't have TAs to cater to regular students right now, and I have no way of restricting the cap to, or say increasing the cap only for executive students. If I had, I would have done that.
But so this can be taken like a request from the students and then it can be done through the backend or something like that.
See,
Maybe
the
you
point
can
is,
run 2
if
courses if possible, sir, because regular student is on the premises. They can take on the weekdays also. I mean,
no,
if
so
possible.
running 2 courses itself, because with some changes, I'm also seeing there's some administrative changes also in play over here. Running 2 courses parallel courses has become very tricky now. So a lot of things are working out. So that's why. Otherwise, I would have been okay to take this up. But the problem is a lot of things are happening over here with a lot of administrative decisions have come in, which has changed a lot of things here.
Sir, please convey our grievances to them.
I'll
Very
most
difficult
likely
for us.
talk to
Sir, we are forced to
Nitin
take
again,
subjects
because
which we see. Financial engineering, why we would do that? I mean, we are forced to take that subject. If you see my course list, there is hardly anything related to data science.
let's see. I'll talk to Nitin once about this thing.
Sir, one possible solution, if I may, sir, if a course is not taken in a hybrid mode, if a slot is given, like it has been happening for the past 2 semesters, exclusive slot for the executive branch, which is YP and XP, these series, X and Y series. So
Yeah,
if
yeah.
that is offered, then a regular student will not be offered that in the ERP
So for
module.
that, you need another. I mean, I will not be able to cater to two courses, no? So you need another
That
faculty
that
member to
that
offer
we
that course.
understand, sir. But that coordination we were expecting that the CSC department might have done for us. That some at least some
So
exclusive slots are given to the executive people, so that they can
so
opt
this,
for
I
those
think,
core
was
subjects.
supposed to be handled by the
Yes, sir.
advisor,
It
but
was supposed to be handled by the advisor, but somehow we have not been able to get in touch. And maybe what you just said, ki sir is slightly new
yeah,
to this
he's on leave
subject.
actually. He's
That's
getting
that's
married, so
possible, sir.
that's maybe a reason why. So maybe ask him out. See.
Sir. Thank you, sir.
Okay.
So one more thing for the final major, the exam will be more of like a MCQ or
No. So it will be like your whatever you, the way in which you give your medicine, no? The questions will be similar to that. You may have some MCQ questions as well, but it will have regular components, regular questions as well.
okay.
Okay. So we have been discussing generative models, and specifically we have looked at Bayes and GANs and conditional Bayes and conditional GANs. And we had started with discussing the cycle GAN, which is a very interesting application of GAN, and which involves translating between one image domain to another image domain. And we are specifically looking at one application where it's an unsupervised image-to-image translation. Okay. And when I say unsupervised, it's basically that given a specific image, say a black and white image, I may not have access to exactly that corresponding image's colored version. So suppose if the task is converting grayscale image to color, I may have pairs of images, say black and white and say colored, but they may not be the corresponding pair. So we have to utilize GANs for this particular purpose in order to achieve this sort of a image-to-image translation. And as we had briefly discussed in the last class, the idea was to basically use GANs, two GANs for the two domains that you have. So if you have multiple GANs, multiple domains, you can also incorporate further GANs. And why the term cycle comes into place, we are trying to achieve something known as a cycle consistency. Okay, so if you remember, we had basically two GANs. So we had two generators and two discriminator. And you had one GAN that was, suppose you had the two domains X and Y. So you had one GAN that would translate from domain X to domain Y, and another GAN that would translate from domain Y to domain X. And you had a discriminator that would be able to identify real images from domain X, as well as the fake images generated by the generator F, which would take images from domain Y and give images from domain X. And the other discriminator would basically do the reverse. It would be good for identifying real images from domain Y, and it would be able to detect the fake images as fake from the other generator that's generated by G. Okay. So during the training phase, the discriminator will check whether the images that are generated by the opposite other generator seems to be real or fake. Okay. And there will be some sort of a cycle relationship. So what we are going to do is basically, suppose if you have a horse image, you would use a generator to move it to a zebra, map it to a zebra. And then what you would do is that obviously there will be some sort of discriminator for zebra as well. But even before doing that, we'll try to get back the corresponding horse image and the discriminator for horses, and you will have the discriminator for your zebras. So you're sort of like you're achieving a cycle in that way. So this is suppose same thing. So it's, in a way, you're achieving a cycle. So you have a discriminator for identifying horses, you have discriminator for identifying zebras. So this discriminator ensures that the horse that is converted to a zebra is actually a zebra, looks like a zebra. And this discriminator ensures that this particular horse that you get back is actually still a horse. And so in a way, you're achieving, you're trying to achieve some sort of consistency in a cyclic manner. So you have a cycle consistency. So I think we had looked up to this point, right? So one training sample of the cycle gun will be formed by the random picture of a horse and a random picture of a zebra. So you don't have corresponding pairs. So you'll take, say, any picture of a horse and any picture of a zebra. The generators will take an input image. The horse generator will take the horse, the generator which maps from horse to your zebra will take image of a horse here. And the generator that maps from a zebra to a horse will take the zebra image as input. And then it will produce the corresponding image on the other domain. Discriminator will basically predict whether that particular image that is getting is real or fake for that particular domain. So even a real zebra image will fail DX because DX is only looking out for horse images, and a real horse image will fail a zebra discriminator because it's looking out for a zebra. Okay. Now, this is the mapping that we are trying to achieve using these two generators between the two domains. And in order to enforce cycle consistency laws, what we are basically doing is that once you're mapping from your, say, horse to a zebra, you're mapping back to a horse. And so this is how it will look like. So g of x will give you your zebra, and f of g of x will give you back the original horse. And this particular reconstruction, in a way it's a reconstruction of this particular image and the initial image should be consistent. They should still refer to the same horse. And as a result, if you can enforce this thing, anyways, you have both the discriminator that is forcing the other generator to produce a good image of this particular domain. And with the cycle consistency, you are also ensuring that you can get back the original image. So in a way, you're because you don't have sort of exact supervision in this case, so your indirect supervision is trying to get back the same image of the horse, given that it has been transformed to a zebra first, and then you're transforming back to your horse. So indirectly, you're providing this supervision. Okay. So this is why it's known as a cycle GAN. So in sort of, you can see a cyclic relationship that is happening between, any sort of a training pair, right? And this will be the objective. It looks a bit complex, but it's actually, you can actually divide it into three different parts. If you look at the first part, it's basically you'll be applying some sort of a GAN loss where you have the generator that moves from a domain X to domain Y, and you have a domain Y discriminator, and you're basically moving from X to Y. So that's the domain information. You have the other GAN, which takes the generator F and uses the domain discriminator for X, and you're basically mapping from Y to X. So this generator F will convert your image from the Y domain or the zebra domain to your horse domain, and you have a corresponding horse discriminator as well. So this will be a generic GAN losses, and you also have this cyclic consistency loss, which will basically involve that you take one same image, convert that horse image to a zebra image, and then you convert it back to the horse image, and you should get back the same image or close to the same image. Okay. So as I mentioned, these are the three parts of your loss. You have your adversarial losses for each domain and a cycle consistency loss. So adversarial loss, if you remember, this is the standard loss of your discriminator, your GAN, where you are, for your discriminator, you'll try to maximize this loss. Basically, for real data, you'll try to make this close to 1. And for fake data, that is the one that is generated by G, you will try to move it closer to 0. Whereas in the same loss, for the generator, you'll try to basically take the minima of the setup. So if you try to minimize this thing and minimize this thing, effectively you are ensuring that the discriminator output is high or close to 1 for your fake images as well. So both of them are playing to fool each other. Similarly, you have a similar loss for the other domain as well. So you have from X to Y, now you're from Y to X. Okay. And this, at least up to this portion, it's similar to that of a GAN. And then you have your cycle consistency loss, which is you take an image, you map it to the other domain, then you bring it back. And after you bring it back to the original domain, you should get back the original input. Okay. So this will be your cycle consistency loss, where you're basically doing G of X, then F of X. So you should get back your original image, whether it's the horse image or the zebra image, and you're trying to reduce this loss as well, along with your general GAN losses. So this is actually a very handy procedure and allows you to do a lot of things. I mean, when CycleGAN came into play, it opened up a lot of new possibilities of conversion, image conversions from one image to the other. You have day to night images. You have you can change the weather of a given, say, image that you have. You can colorize images. You can improve the quality of an image. So you can consider any image to image sort of translation improvement, and that you could achieve through CycleGAN. Okay, and a very interesting application of this was basically converting a proper satellite view image to, say, image which only highlights the roads and the particular map, and then you again try to get back the original image. So it's a very interesting application of this thing. In general, you will find a lot of applications of this sort of CycleGANs, and there have been further work on this idea of cyclic consistency. I mean, image to image translation, but this was a very popular idea of CycleGAN. Okay.
We used to improve the like lower resolution image to higher resolution image.
Can you repeat your question?
So can the CycleGANs be used to convert a lower resolution image to a high resolution image?
You can, but then I mean, that is instead of performing super resolution, you're trying to do that. But then you would have to be very careful how you design your discriminator. So your discriminator, because the image basically is still remaining the same, the discriminator should be able to differentiate between a low quality image and a high quality image. So that's your discriminator will have to be trained in that manner. And if you can achieve that, then that's fine. I mean, this can achieve any sort of translation, and with it doesn't even require exact, set of pairs of, say, from both the domains. You can have different pairs from different images, different domains, and still be able to achieve this sort of a translation. Okay, but then for any GAN, the quality of the images that you end up generating will depend heavily on the discriminator. Okay. So if your discriminator training is fine and it's able to differentiate between two types of same images of different quality, then it's fine. Your generator also will be able to catch up and give you good images.
Okay, sir.
Okay. So this is one example which I thought I should show you. It's a very dumbed down example of a CycleGAN so that I can run it locally without much resources. Right. So, I mean, for this purpose, I created a synthetic data set where you had, I think, a circle, or in this case, I think we don't have a circle. We have squares and triangles. Okay. So one of the domain will only have square images. The other domain will have circle images. I have mentioned circle, but actually I changed this shape later on. So if you ignore that part, this is simply data generation. The generator part, if you look at it, it's a simple FC fully connected layer-based generator. There's nothing special about it as such. You have a discriminator which will take your input image and basically give an output size of 1 and determine whether it's a real image or a fake image. But what is interesting is that we'll now create two such GANs and two such generators and two such discriminator, one for each of the domains that we have. Okay, in this specific case, you have two different shapes. So you have one generator and discriminator for squares, and other generator and discriminator for triangles. Right, and then when you move to training this setup, you will have to anyways calculate your GAN losses for both the GANs, but you'll also have to include a cycle consistency loss. Okay. So if you look at the first case where you're taking real X images, so you have two domains, real X and X and Y. You take real X images, and your discriminator for X should be able to identify that. Okay, and for discriminator Y, you take the real Y images, and your discriminator should be able to identify those. Now you take the fake Y images. How are you generating the fake Y images? You are using the generator, which in this case can take the image itself as an input. And based on the image, X image, it's giving you a fake Y image. And the discriminator will try to output a fake label for this fake Y image. Similarly, the other discriminator will try to output a fake label for the fake X image, depending on how, from both the ends, you're trying to do the same thing. And if you notice over here, this will be the total loss that you get for your discriminator, which is nothing special as such, but just twice the losses that you used to get, because now you have two discriminators. So you have lost dx real and dx fake. You have lost dy real and lost dy fake. So same thing twice. For the generator, you will have, what you can do is that you can take your fake y that you generated over here, which was generated from a real x, you went to y. Now you can get back the reconstructed x and apply a loss on top of the real x and the reconstructed x. That will be your cycle loss. And you can do the same cycle loss for the other domain as well. And the generator loss will we try to basically fool the discriminator. So for the fake images, y images, you will try to optimize the generator from x to y so that the image is so good that the discriminator for y is fooled. Similarly, over here, you're trying to fool the discriminator for x. So at least this portion, which is your G loss or generator loss, is basically, at least up to this portion, is your standard G loss, and this is your standard discriminator loss. But on top of that, we also add the cyclic losses, which is basically you take an image of x, you move to the y domain, and you come back to your x domain, and you see the reconstruction loss. And same thing that we can do for y as well. Okay. And finally, when you have all of these losses, you optimize this particular setup. Okay, and you get something like this. It's able to convert at least the squares to your triangles, or say triangles to your squares. But the position thing, it has not yet learned, because it's a very basic 2-3 layer network, and it's a fully connected network. So at least the spatial information may have not been incorporated well enough for this to actually specify the same position for the generated images or the converted images. But it is actually able to achieve good translation good transition from the square image to your rectangles. Okay, maybe if you use a convolution layer and maybe optimize this much further, you will be able to obtain the required exact translations as well. Okay, so that was a simple example of CycleGAN. If I come back, yeah, okay. So I think we don't have much time, so we'll just discuss your VAE GAN. So as the name suggests, it's a combination of VAEs and GANs, because these are the only two types of generative models that we have seen up to this point. And both have their own mechanisms. So VAEs will have an encoder which gives you your mu and sigma, sort of something close to a normal distribution, and then you sample from there a Z and use a decoder to get back the original image. But over time, you ensure that this particular distribution follows a normal or Gaussian distribution, so that once you have done training, you can simply randomly sample from your Gaussian distribution and pass it to your decoder to get new images. So that was your VAE. GAN, on the other hand, took a different approach. It directly sampled from some uniform or say Gaussian distribution, generated an image, and it did not try to mathematically improve this image. Rather, it simply passed it to a discriminator whose job was to detect between real and fake image. So your GAN learns to generate good images so that it is able to fool your discriminator, while your discriminator is always trying to identify the actual real images and also identify the fake images separately. Okay, so we are trying to combine both of these ideas. There are many ways of combining this. You can simply take this VAE setup and say directly give the output to your discriminator, and then expect that this particular setup still holds. And whatever images you're generating, remember that for VAE you are getting comparatively blurry images compared to say GAN images. So using a discriminator, that will ensure you or help you to get much better images using a combination of VAEs and GANs. Okay, and Right. In order to achieve this thing, and this is from a paper from ICML 2016, it's a very famous paper. And the idea was that you don't use any sort of a reconstruction loss as such. I mean, so your discriminator is a very useful network. So no matter what kind of generator network you use, to generate any sort of data, a discriminator always ensures that you are close to the real data, because discriminator actually gets to see real data while it is training. So if you have to fool your discriminator, you have to also be similar to a real data. That way, a VA GAN utilizes this property of, at least the discriminator of your GAN to improve its image quality at least, and you are supposed to get much better images as compared to a simple VA. Okay. And also one other advantage of using, say, a VA GAN is that generally a GAN is very difficult to train. For smaller images, it may still be easier to train. But comparatively, since VA is sort of taking an input image itself, and then you're, reconstructing back an image and then passing out to a discriminator, this component can be either considered entirely as a generator, or you can consider the decoder of your VA as a generator. And but since this generator actually gets a proper structured, say, way of input rather than simply some noise, so it is much easier to train compared to, say, a random GAN where you are randomly giving it noise and asking it to generate new good images. Okay, right? So what we end up doing is that at least in the original VA GAN paper, what they do is that they take a standard VA and so remember, the VA had two losses. One loss was to ensure that this particular intermediate values are coming from some random some Gaussian distribution, and the other loss was the reconstruction error loss. So you're inputting X and you're getting back X bar, so you will then try to get a reconstruction error. So these were the two losses in your VA. What this original paper did was that it retained this regularization loss, but it removed the reconstruction loss, and instead it passed the reconstructed image to a discriminator, and the discriminator job was to basically say whether it's real or fake. So now if your VA is producing some image that is not a very good image, maybe it's a very blurry sort of an image with not enough details, then your discriminator will start identifying that this is a fake image because it's not matching with the exact distribution of, say, your real images. Okay. So that way, instead of looking at a reconstruction, you're looking at whether it's a realistic image or not. Also, what this ensures is that VAs had a tendency to not have too much diversity in its output, because VAs are always being trained for reconstruction. So whatever image you give, it's trying to reproduce that itself. So with this, you're also infusing some diversity in these images, because if you remove the reconstruction term in the loss for your VA GAN. However, there are implementations where you still retain the reconstruction term of your VA, but also you have this discriminator on top of it, so that you get to also further improve the quality of your output image using your VA GAN. Okay, right. So, okay. So with this, let's come to the next idea. We don't have much time, so I will just discuss it and maybe look at the implementation tomorrow. So, as mentioned, GAN is a generative model, so it can generate any type of data. Provided you can provide a good representation for it. So if it's an image, you already have a good representation in terms of pixel values. If you have a text, you need some other version, some embedding of that particular text, so that you can then utilize that text and generate something, and which is what we'll be looking at, which is a text to image synthesis using a GAN. Okay, and which is very popular nowadays. Even though you're using maybe more of diffusion models, which we'll look next, in order to generate good images from text, but even with a GAN, it's a very, GAN is such a versatile platform. You can also use it to generate text from images, and this will be a very maybe low weight or low computation model to achieve this sort of a task. Okay, so what we can do is that we can take some description of your images and convert it into some textual embedding. For that, you will not use a GAN. You will maybe use some pre-trained either say a Word2Vec or some other embedding model that is available for your text. But once that is there, we have already seen something known as conditional GANs. So if I take a simple GAN and also add a condition along with it, I can ensure that the images that are generated are images that follow this particular condition. Okay, so something like this we've already seen, at least say for say we did it for I think for MNIST, where we gave the input condition as the number that we are trying to generate, and this was able to very well start generating the images itself for that particular number, whichever condition we are giving. So text to image synthesis can be done in a similar manner. The only difference now being is that the condition that you give will actually be the text or the embedded version of that particular text or some description of that image. Okay. So this condition, remember, even for a simple conditional GAN, we had to provide this condition to both your generator as well as your discriminator. Some of the methods actually give this particular condition much later on, at a much later layer of your discriminator, when your say feature size has become very small, or you can also give it maybe initially. In that case, because it's an image that you generally feed to a generator, so you'll have to add another channel maybe, or maybe 2-3 channels in order to represent your text embedding. So it's a better way that you give your image only to your generator first, your discriminator first, and after a few layers, when the feature sizes become small enough, then you incorporate that particular condition in your discriminator. Okay, concat that condition, and then you do some further processing. But at the end, your discriminator will give you true only if you have generated the correct image for the correct label or correct condition. Even if you're generating a correct MNIST image, but you're not generating the image from the required condition, then it will give you a false. So that way, it's not only looking for correct images, but it's also looking on images that are supporting the condition or that are following that particular condition. So your positive samples for your discriminator will be real images that match the textual description. The negative samples will be real images that do not match the textual description, also fake images that that has been generated by your given GAN. Even though it matches the textual description, if it finds it to be fake, it doesn't matter, it will give you a false. Okay. And the network will, I think the initial paper that I was mentioning would look something like that, where you have this generator network, where at least while providing the noise and some description embedding, you would do it at the beginning of the generator network. But when you get an image, you feed it to your discriminator. You don't immediately add the condition. Once the size of the features have become small enough, you add your condition. Because at the end, this word embedding will simply be a vector, a 1D vector. So you can choose where to append that 1D vector within the network. And then following that, you will have some more, layers. And finally, you get your output at either 0 or 1, depending on whether it's a fake image or a real image. So, in terms of training, you're still doing something similar to a standard GAN itself. Okay. And except that you will have a slightly different set of, say, positive and negative samples. Okay, because you have incorporating the condition as well. So if you are picking a real data and the corresponding correct label, then your discriminator will try to give you 1. Whereas if you're picking a fake image, even though if you have the real embedding, the discriminator will try to give you 0. And if you're picking a real data, but you're picking some wrong description, then your discriminator will try to give you 0. Whereas your generator will try to do something opposite. It will try to reduce this particular setup while try to increase this, so that the generated images actually gives you 1. Okay, and that way, both of them are again playing against each other. Just that, it's similar to GAN, just that the samples on which you will be playing this game will become slightly different. You're also considering the condition as well. And this is able to, I think, get good enough sort of results. And if I simply show you this particular network, and after that, which you can end, we can discuss this tomorrow, but I'll just show it to you. So in terms of network, if you look at the network, it's a standard GAN. Okay. And in this particular case, since I'm using a FC layer, I have incorporated the condition at the first layer itself. If you have a proper complex convolution layer, you may choose to incorporate this particular text embedding maybe later down when the feature size is small. Okay. And we have the same standard MNIST dataset, except since we did not have some text for the MNIST dataset, I'm introducing some deliberately mentioned some text like this is 1 or this is 2, something like that. And we are using embedding. We're using a word2vec model. It's a very standard, it's old now, but it's a very standard word embedding model. And it takes any sentence, set of words, and converts it into an embedding. And given that embedding, now the rest of the training is similar to your conditional GAN, where you will pass both the real image as well as the condition to both your real image for your discriminator. For your generator will give noise and the conditioned embeddings. Okay, and as you can see, there are two types of fake losses. So one fake loss is fake image and the correct embedding. Other is the real image but the wrong embedding. And both of these things discriminator will try to show as fake, whereas your generator will try to do the opposite. It will try to take the generated images and will try to make the discriminator output the real labels for the generated images. And this way, both of them play against each other. And at the end, if you maybe give a description like this is 2, then it's able to generate the 2 image. Even though it's a very basic, it's nothing special about this description, but for MNIST, we did not have any other information. So we had to do with this particular setup. Okay, I think we are done with the time at least. Any doubts up to this point?
Sir, hello.
Yes. Yes.
Sir, can you extend the deadline of assignment?
It's a very small assignment, so it's already it's on Tuesday, I think.
Yes, on 12th.
It's a very small assignment. You don't have to do much changes to it. Also, most of the things are already mentioned. What you have to exactly do at every step.
Mhm.
So maybe try it out. If there's still some issue, then we can look into this.
Okay, sir.
Okay. Fine then. I think. Just a second.
Thank you, sir.
I'll upload the notebook on Classroom. Okay, then I'll stop the recording and we can meet tomorrow. The rest of